Hello, welcome. I'm glad so many people wouldn't be scared away from what I said 5 minutes ago. I'm going to talk about quantum information, and there's nothing new in what I say today. I just want to give you a gentle introduction containing some technical details so you get a first idea how information in the quantum world is fundamentally different from information in our classical world that we're used to. My day job is I work for Theoretical Mathematical Physics Master Program at Ludwig Maximilians University in Munich. So if you want to hear a lot more about this, come to Munich and enroll in our master program. Okay, so, but before we get into quantum, I have an overview. So before we get into quantum physics, I want to settle a bit of almost trivial background on classical cryptography. And I should say also, the area of quantum information is very wide, and I should also say it's not my own area of specialty. It encompasses lots of different things, in particular quantum computing and quantum cryptography. And I decided not to talk too much about quantum computing because, basically there are a couple of algorithms that would be a bit hard to explain, and I think it's much easier and much clearer to talk about quantum cryptography. And that's what I'm going to discuss today, and that's why I'm going to talk about classical crypto first. The other thing is, as I said, I'm a theoretical physicist, so I'm interested more in the mathematical structures that we encounter rather than the actual thing. So, but there's also a huge difference between quantum cryptography, which is something that exists in the real world. You can buy off-the-shelf quantum crypto devices these days. I know last year we had talks here about how they can be compromised, but quantum computers do not exist. There exist prototypes, and as I'm informed, kind of the largest job that has ever run on a quantum computer is the factorization of 15 into 5 by 3. As you can understand, so this is also merely a demonstration rather than of practical use, because on my MacBook Pro I can factorize much larger numbers. So I don't gain a lot from the theoretical advantage of quantumness in the case of the quantum computer, but for quantum crypto, as I'm going to explain to you, you can get a real advantage because you can prove that there's no eavesdropper. And I'm going to show you how that works. Okay, so I talk a bit about classical crypto, then I have here my, oops, don't point with the laser pointer at people. I have here my little experiment. Great hand of applause for my guinea pigs. Okay, so these two things will be my warm-up, and then there'll be some heavy-duty mathematics machinery in the middle, and I try to make it as little demanding as possible, but we need some formalism, otherwise I would just telling you prose and would just advertise the thing rather than explain it. So I decided to torture you a bit with formulas for the price that you can gain actual understanding, hopefully, of this. And then from this I can then explain how quantum crypto works. And then if there is time in the end, I'm going to elaborate on the question whether the human brain is a quantum computer or not. Okay, so classical crypto, basically the essentials of classical crypto work like this. The archetypical example of cryptography is a one-time pad. So here are my friends Alice and Bob, and they want to transmit 1 bit of secret information. So what they do is, one of them, say Alice, turns off the light in her bedroom and goes to a drawer and picks a pair of socks. Okay? So the nice thing about the socks is that she ordered the socks after washing them. So there are either 2 red socks, or 2 green socks. Right? But the thing is, there's never a red sock and a green sock. So she grabs, at dark, she doesn't see the color. She grabs 1 pair and gives one of the socks to her friend Bob. So here, in this case, you can see on my slide, she has picked the red pair, and the green pair is still in the drawer. Right? So that's their secret key. The secret key is the color of the socks. And since she picked the red one, she knows the code is now, if she picks a red sock, she transmits the opposite of the message. She says, not message, right? And then Bob knows also the code. He sees he has also a red sock, therefore he knows Alice has a red sock. Pretty trivial. So he knows not message is the message. Okay, so much everybody knows, right? That's not very hard. That's very effective. That's really secret, unless our eavesdropper Eve got hold of a copy of the sock. Right? She also has a red sock because she managed to put a third sock in the drawer and get hold of it, and therefore she knows not is the message that Alice wanted to transmit. Okay, that's classical crypto one-time pad. Everything trivial so much, but let's abstract from this a little bit. So what they use here is that the sock pair that they share is in a correlated random state. Right? That's essential. So it has to be random. It wouldn't work if all the socks were red, right? Then there wouldn't be a code. Right? It has to have this random element, so Eve cannot guess which one they pick unless she gets a copy. And it also has to be correlated. That means in 50% of the probability, they pick 2 green socks. 50% of the probability, they pick 2 red socks. But with 0% of the probability, they pick 1 red and 1 green. Okay, so that is the essential thing. So it's random, so nothing is here 100%. And it's correlated, so the 2 colors of the socks are always the same. And the important thing here is also that this state has to be, I'm using highbrow language for a trivial thing. This state has to be prepared by a trusted entity. So either they do it themselves or they have to do the sock distribution, like sending it by mail. They have to trust the mail system, right? If Eve is the mailman and looks into the envelope, sees the color of the sock, then they're lost, right? And of course, there's a further assumption, and that'll also exist in the quantum case, because otherwise you're completely lost, that public communication is reliable. So, here, back, she has to announce not message, and Bob has to be able to hear this message and to hear it correctly. Otherwise, it wouldn't work. So, okay, forward. Okay, that is the classical situation. Now I want to show you how to improve this in the quantum situation. But to be able to understand this, I have to explain a little bit of quantum mechanics first. And here's our little experiment. So I give you the theoretical experiment first, and then we do it in real life. So my experiment consists of a box. And the box has a handle that has 2 positions, A and B. In this case, the box is here, and this is the handle. So it has a position left and it has a position right, and left and right, and left and right. It has a slot where something can be added. That's on top here. You can't see it. And then it has a pointer. So, and how does it work? So my experimenter, here are my guinea pigs, thank you very much, decide randomly to pick one of these positions, A or B. Okay, A or B, or back A. And then, so these describe 2 possible measurements that my machine can do. I can either I can do a measurement of the A aspect of the thing I'm measuring, or I can do a measurement of the B aspect of the thing I'm measuring. And then I add the thing, and then the pointer points either to the -1 or the +1 direction. Okay, that's all I have to explain about. This is how the experiment works. And the thing is, I do not do it once, I do it 3 times. And I distribute the things to be measured from a central origin. So that is what we're going to do here. Maybe we do this once. So Philip has already pressed his button. So let's reset the whole thing. Okay, so because you probably can't read, here is an LED display saying either plus or -1. You can't read this. Thanks to Munich Chaos Computer Club, they provided me with these 3 lamps. So the lamps can be either red or green, and it's green if it's +1 and it's red if it's -1. So you can better see what they're doing. So if I may ask you now to run your experiment, measure your glass of water that I gave you. And you see it because the blinking stops. Okay, so now you see, so first of all, you observe that all the pointers are pointing in the right direction. So all pointers are measuring B, and we measured -1, +1, -1. Okay, so that's pretty much random at this point. But now we do this over and over again, and we change the switches and we memorize what the results are. Okay, and the thing, I mean, maybe I give away the message is that we are going to find a correlation between these measurements that I will argue is impossible in a classical world, but then later argue that it can be achieved. I can build such a machine in a quantum world. And then this proves, if you like, that the classical world is not quantum, because I can build machines that I can prove are impossible in a classical world. Okay, so let's do a couple more measurements, gentlemen. So here we have A, here we still have B, and we here still have B. And you see +1, -1, -1. Let's do it again. Maybe you leave the handles for a couple of times and just do more measurements. Just leave it with A. Okay, now we have -1, -1, +1 over there, and again. Okay, so, and we keep a logbook, and we do this over and over again. And once we do this, we get a table like this. Okay, I've done this at home. I promise this is the real output of this. Okay, so you see here, I'm sorted the results already. Here, in this case, everybody had their handle in the A position. So we measure A 3 times, A1, A2, A3, and you see plus, minus, plus. And then plus, minus, plus, and then minus, minus, minus. In this case, the first 2 switches are in the A position, the last one is in the B position, and so on up to here, where the last one, where everybody had their switch in the B position. So now the question is this pattern completely random? Well, it's not. I promise it's not. Who sees an aspect that is not random? Okay, maybe you focus on these columns. Okay, somebody spotted that there's no plus, plus, plus in this column. Very good, that's true. Very good. Is there anything else that is missing in the first column? Single pluses. Okay, so there are no 3 pluses and there are no single pluses. So everything here is either a single minus or 3 minuses. Okay? So, and what about the green columns? Yeah, so you spotted the difference, yeah? No. Well, this is plus, minus, plus, this is minus, minus, plus, so. No, this starts out with plus, plus, plus. No, this one doesn't agree. Yeah, so somebody said in the back, it's the other way around, right? So in the green ones, there's either a single plus or 3 pluses. Okay, does everybody see this? So let's summarize this. If I measure A 3 times, I have an odd number of minus signs. Okay, let's do this in real world. Let's measure A, everybody. Everybody put their handle to the left. To the left, and then where's my reset button? Okay. Okay, let's measure the thing. -1, +1, +1. A single minus sign. Let's do it again. -1, +1, -1. One more time. Maybe we get 3 minus signs. -1, -1, -1. Okay, you see, there is always, oops, once more, there is always an odd number of red lamps. There's always an odd number of minus signs. Okay? And in these 3 green columns, these are the columns with 1 A and 2 Bs. Okay? So maybe 2 of you switch. So now we have 1 A and 2 Bs, and we measure again. Now we should have an even number of red lights. So 0 is an even number, and 1 more. Okay, and 2 is also an even number of red lights. So the real experiment does indeed what I promised to you. Okay, so let's formalize this. Now comes the math. So we have when I measure 3 A's, I have an odd number of minus signs. So if I call the variables A1, A2, A3, this just means that the product of A1, A2, A3 is minus 1. Right? And similarly, for an even number of minus signs, a product of 1A and 2 B's is plus 1. That's what I just said, or in the other 2 combinations. Now we can, if A1 times B2 times B3 is plus 1, and everyone is either plus or minus 1, I can say that's the same as A1 being the product of B2 times B3. Either A is plus, then the product has to be plus, or A is minus, and then the product has to be minus. That's pretty trivial, right? But now from these 3 formulas here, I can multiply these 3 equations. So I get A1 times A2 times A3, and then you see that every B appears twice. So this is B1 times B2 times B3 squared, and any square is a positive number, so the product is plus 1, but we said it should be minus 1. Okay? So this is my contradiction that I was talking about. You can compute from these experiments, you can compute the values of the product of 3 A's, and what you compute is plus 1, but when you actually measure it, it's minus 1. Right? Therefore, something is wrong. Right? This cannot be true, that there are these variables that have these properties. Okay, so in particular, this cannot happen for local, realistic measurement. So what realistic means, that's a technical term I'm going to explain later, but local, I have to explain. So local means that what Philip is measuring here on his first station only depends on the position of his handle and the contents of his water glass. Right? So everything and it could contain a random element. Here maybe there's a coin flip inside the box that determines the outcome, but it can take only into account the position of the handle and his water glass. So that is the assumption that goes into my little calculation, that what he measures when he puts the handle in the A position is the A measurement on his water glass. Okay? Now I explained to you that this experiment is impossible, but I showed it to you. Right? So something must be wrong. Well, of course, what is wrong here is that this is not a quantum experiment, right? There's an Arduino inside and blah, but it's not local. They're connected by cables, right? So in reality, my true experiment, this box knows about the handle position of the other 2 boxes. And therefore, I can show you this on stage, even if it's not a quantum computer, because it's not local. This box measures, if you like, also the aspect of the handles on the other 2 devices. But if I assume that I only do a local measurement, then I just derived for you that this is impossible. Okay, is everybody confused now? More than you would like to be confused? No, great. Okay, so let's go on. So now let's get into quantum mechanics. As I said, I have to explain a very little bit of quantum mechanics to explain to you how this works. So again, I'm going to use the abstract language that I started out using with the SOCs. So first of all, there are states in my system, and in quantum mechanics, a state is represented by a vector. So what is a vector? A vector is 2 numbers written, well, in the simplest case, is 2 numbers written on top of each other and put parentheses around them. That's a vector. That's enough for you to know. And it's it's usually you use Greek names, so let's call this one psi. And for the case that you just write 2 numbers on top of each other, this is called a qubit. I mean, that's for quantum bit, if you like. And there's one further condition, and that is that the absolute value of the first entry squared plus the absolute value of the second entry squared has to be 1. So let's look for examples. The examples I'm going to use in the following are the ones with 1 zeros, and this of 1 squared plus 0 squared is 1, so this fulfills this condition. And usually, I want to call this state, I want to call up. So I draw an up arrow. Okay? And I could also have a 0 and a 1 instead of a 1 and a 0. And I want to call this right. And these are kind of the two states, the two simplest states that my system can be in. I haven't talked about how I realize this, the state of what kind of thing this is. If this is an electron spin or something else, there's one thing you might know that has exactly these states, and that is polarized light. So if you have light, which is an electromagnetic wave, then it can either oscillate, the electric field can oscillate, I mean, the light that from this light comes to me, this can either oscillate in the vertical direction, or it can oscillate in the horizontal direction, right? And if I can use a polarization filter to filter out, I mean, this true light is a mixture of both, but I can use a polarization filter to block out these two components. So either I have the filter in this direction, then only the horizontal polarization gets through, or I put it that way, and then only this component gets through. This is used in old-style 3D cinemas, for example. I hope everybody has seen a polarization filter in their lives at one point or the other. If you have an LCD display, you own one. Okay, so that is how I describe the state of whatever system I want to discuss. And then, of course, the system is not alone there in the world. I want to observe it. I want to do measurements on this. And I also have to formalize how these measurements work. And of course, I can do several different measurements. Like with the socks, remember I had socks. I can measure the color, or I can measure the size. Right? And so also in the quantum world, I have different measurements. And all my measurements, like the states were vectors, are now represented by matrices. Here I have 2 by 2 matrices, again with the condition, the technical term is that it has to be Hermitian. But let's not worry about this condition, because we only need 3 examples. Okay, my first example is I, the so-called identity matrix, which reads 1, 0, 0, 1. This fulfills this condition. This matrix, when I apply it to a vector, you all promised to me you applied matrices to vectors before, right? Then you know this matrix leaves the vector as it is. It does nothing. That's the identity matrix. Then I have this matrix that I want to call Z. Z looks like this one, except it has a -1 in this position. What this does, when you apply it to a vector, is it leaves the first component intact, and the second component gets a minus sign. Okay, that's the operation that I do with the Z operator. And then I have an X operator that looks like this, has the ones and the zeros swapped. And what it does with the vector, it flips the components. It puts the upper component in the lower position and the lower component in the upper position. Okay, these are my 3 measurements or observables that I need in this talk. Okay, so now I have a state and I have measurement. And of course you want to know, I mean, we want to predict stuff, right? So if I have a system in a certain state represented by a vector and I do a measurement represented by a certain matrix, you want to know what is the outcome. And the problem is that's difficult. But you can be lucky. And you're lucky particularly if the state psi happens to be what is called an eigenvector of M. So what is an eigenvector? An eigenvector is such a vector that when I apply the matrix to the vector, I get the vector back multiplied by number. I mean, lambda is just a number. So the only thing the vector does, if you think of the vector as an arrow, it can only change its length, but it doesn't change its direction. Right? So I apply the matrix to the vector, and what I get out is lambda. There is this number lambda, such that the result is lambda times v1 when it was v1 first, and it's lambda times v2 when it was v2 first. So the first line, this number and this numbers are always multiples of each other. But the important thing is that the lower numbers are multiples with the same multiple lambda. Okay? If this happens to be the case, if psi happens to be such a vector for this matrix M, then the outcome of the experiment is very simple, because the measurements yields lambda. Whenever I measure this matrix M in this eigenvector psi, I always find the result lambda. Okay? Let's see examples of this. So let's take our matrix Z, which was 1, minus 1, and I take my vector up. And I see that clearly this is an eigenvector, because remember, Z multiplies leaves the first component intact and multiplies the lower one by minus 1, but the lower one was 0, so nothing happens here. So indeed, this up is an eigenvector with lambda equals 1. Okay, so I will always measure 1. Similarly, my vector that I wanted to call right, the one with 0, 1, measured in Z, gets here a minus sign, so lambda is minus 1. So in this measurement, my result will always be minus 1. But if I have a general vector, then I get v1 minus v2, and unless one of them is 0, they don't have a common multiplier, right? Everybody got that? Okay. In short, Z applied to up is up, and Z applied to right is minus right. Okay, next example is my x. Remember, x switches the component. So here you see v1, v2 gets mapped to v2, v1. Okay, how can it be a multiple of itself when I swap the components? Well, trivially, if both components are the same, right? Then if I switch the same numbers, I don't do anything at all. So, okay, here are square roots of 2. Whoever is afraid of a square root, you can safely ignore all the square roots in this talk. They're just there to make the thing correct in the formulas that I write. You can completely blind them out. They're not important for what I'm going to say. Right? So if you can read this as 1, 1 if you're afraid of square roots. It won't change the meaning. Okay, and I want to call this, because this thing is kind of half up, half right, I want to call it upright. Okay? This has the same components here, and therefore if I switch them, if I flip them, I get the same thing, so lambda is 1 in this case. And for up left, I have opposite equal components here, and if I flip those, I get minus 1. So these two diagonal arrows, these are the eigenvectors for my matrix X, for my flipping matrix X. Okay, so that was the case when I have eigenvectors, but not every vector is an eigenvector, right? So, but in the more difficult situation, there's hope in terms of the spectral theorem, and that tells you whenever I have some m, and then I can always find two such eigenvectors. Right? There are always psi1 and psi2 and corresponding numbers, lambda 1 and lambda 2, such that these are eigenvectors. And then the most general state can always be expressed uniquely as a weighted sum of these two eigenvectors. So these are the two eigenvectors, psi1, psi2, and I multiply them by some weight, by some number, and then add them, and every psi I can write in such a way for the correct values of C1 and C2. Okay, so what I have to do for my general state, I have to write it in this way, and then if I do the measurement, now comes the fundamental difference in quantum mechanics, then the result is probabilistic. I measure sometimes lambda 1, and I measure sometimes lambda 2, with a certain probability. And the probability is given by these numbers C1 and C2, in particular, so it has to be C1 squared and C2 squared. These are the two probabilities for measuring these two outcomes. And that's true randomness. You cannot look inside it and discover the mechanism how the randomness works. This is true quantum randomness. Okay, by the way, mathematics makes sure that the sum of C1 squared and C2 squared is always 1. So with probability 1, you get one of these two results. Okay, and then when I measure, let's assume I measure, the outcome is lambda 1, then that's also new in quantum mechanics. The measurement changes the state. I cannot do a passive observation of the system. When I do this measurement m, and I get lambda 1, afterwards, the state is not the same anymore, but the state is changed to the state psi 1 that corresponds to lambda 1. And if my outcome was lambda 2, then after the measurement, the state has been changed to psi 2. Okay? So that is how measurements work in quantum mechanics. Okay, let's see this in the real world in an example. We saw that the state upright for x, this was an eigenvector for x, that was the one with two equal components, so it always yields 1. But now I want to measure z on this, so this one upright was this vector, and remember these two guys were the eigenvectors for the z measurement, and this is the way to write them as a sum of these two vectors. And you see, I mean, these 1 over square root 2 and 1 over square root 2, these are the numbers that are called C in the slide before. So the result is either +1 if I measure this one, or -1 if I measure this one, each with probability 50%, because if I square 1 over square root of 2, I get 1/2, and that's 50%. Okay, so if in this state, the eigenstate of x, I measure z, the result is like a coin toss. It's half of the time I get +1, half of the time I get -1. And after this measurement, I'm either in the state up or in the state right. Okay, because again, I write them in this way in terms of the eigenvectors. And if after doing this z measurement, I then measure x again, I'm either I'm either in the state this plus this, or in the state this plus this. And then also, if I measure the z, then also the x measurement will be random again, right? Because I changed the state, and after measuring z, the state is in this half +1, half -1 state with regards to the measurement of x. And that shows us that x and z, if you like, I measure the x value and the z value of the thing, they cannot have an exact value at the same time, right? If it's in this state, then I have an exact x value, but a random z value. But after the measurement, I have an exact z value, but a random x value. Okay? So that's the crucial property of quantum mechanics, that is possible, that things, that certain measurements cannot be exact at the same time. Okay, so let's generalize this quickly to bigger states that have more than one component. So I could have n of these systems that I was talking about before, and then the state looks like this. So each individual one is in the state psi 1 or psi 2 up to psi n. Then I write this fancy tensor product sign in the middle, which doesn't have to concern you. And then I can have several combinations, and again, I can add them with weights. And then I can, if I have several things, like in this case, I had 3, for example, I can do a joint measurement. So I measure something on each component. So on the first component, I measure M1. On the second component, I measure M2, blah, 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 up to Mn, right? And the result is then just the product of the individual measurements, okay? But in particular, I can choose this trivial matrix that does nothing. If I have a 3-particle system, but I just measure something here on the first one, I can say I measure something on each station, but these two always measure 1. They always do the trivial measurement that always yields 1. That's the same as just doing a measurement here. Okay? Okay, that is the formalism for 3 copies, or in general, n copies. Okay, now the new thing is I can prepare something that's called the singlet state. So this is now a 2-particle system, and I can prepare a state like this. So that is, the first one is in the up state, and the second particle is in the up state, but it's also a sum of the first particle being in the right state and the second particle in the right state. So it's again the sum of these 2 states. Notice, so now we could measure the z component on we do the measurement of z on the first system, so just on this one or on this one. And then you see that here it would yield +1, Here it would yield -1. And in the total thing, it's each with probability 1/2. Right? If I just do one Z measurement, the result is random. It's either plus or -1. But if I measure Z on both components, then this would yield a +1, and this would yield a +1, and the product is +1. And here it yields a -1 and a -1, and the product is again +1. So the product is always +1. So this state is in fact an eigenvector that always yields the result +1 for 2 measurements of Z. That means this state is a random state if I look at each individual component, but they're always the same, right? If I measure Z on both, they can either be both plus or both minus, right? That's like with the socks. The socks could either be both red or both green, and it's like this. But the important thing is, it's also an eigenstate of xx. Remember what x does? X flips the 2 components. So if I flip the one down and this one down, then I flip it with this thing where I get back when I flip the lower one to the upper position, and again. So again, this is the +1 eigenstate of xx. So also if I do 2 x measurements, I measure +1 with 50% probability, or I measure -1 with 50% probability, but they're always the same, okay? But remember that each individual one, I cannot have sharp values on both x and z, but on the combined measurement of 2 x's or 2 z's, I can have sharp measurements on both of them. That's the new thing here. Everybody looks a bit confused. Okay, so I can both yield random results, but they always see the same thing for both types of measurements. Okay, so this is now my quantum version of SOX. These are my quantum SOX, because this observation that I have simultaneous correlated states both in X and in Z is the key to quantum cryptography. Because now my friends Alice and Bob share these 2 qubits in the state that I just talked about. And then later on, they decide randomly if they want to do the X measurement on each. I mean, everybody does the X measurement on their copy of the qubit, or they both do the Z measurement on the qubit. And I just argued that they will get the same result. The result will be random, but they get the same thing. And then they can use this as the color of the SOX to run their classical crypto protocol on this. The result of this measurement is their shared key. Okay? And each one is random, but they cannot be both determined. So, because they have the choice of either measuring X or Z, until they do the measurement, it's random. And that is what helps against eavesdropping. Okay, each one is random, but both cannot be determined at the same time. And that's different, like the 2 measurements I can do on my socks. I can determine that this is a red big sock, and this is a red little sock. I cannot say what the X and the Z component are at the same time. Okay, so why is this better than the classical socks? Why? What about an eavesdropper? So I could have the idea, let's do the same thing as in the classical case. Let's make a 3rd copy. Okay, let's prepare this 3 qubit state with the same pattern. Either they're all up or they're all down, right? And I can do math and see, okay, if you do the Z measurement, indeed, these 2, the first 2 always yield the same Z value, and also the second 2, or the first and the third, yield the same Z value. So in the end, if they all measure Z, they all get the same result. They all get plus, 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 or they get minus, minus, minus. That's not better than the socks where I can make a copy. But if I decide not to do the Z measurement on this, but the X measurement, remember X flipped the 2 components? If I flip this component down and this component down, I do not get this vector here, because the last one, I would get right, right, up, whereas this is right, right, right. So if I just flip the first 2 components, That means I do the x measurement here and the x measurement here and nothing here. I do not switch the components. And in fact, this is not an eigenvector. And I get random results for 2 x measurements. That means in this state, if Alice and Bob do the x measurement, they will not necessarily get the same result anymore for their x measurement. Sometimes they do, sometimes they don't. And this is the result of making this third copy. So Alice and Bob can determine that there is this third copy by both doing the x measurement and announcing the result. And they do it, they don't have just a single set of qubits, but they have many of this, so they do this many times, and if they have the true secret 2-particle state, then they will always measure the same thing. But if they have this one with a third copy, then there will be results where they measure 2 different things, and they can this way detect that there's a third copy, and then can reject this state and say, we can't do cryptography with this, there's an eavesdropper. Okay? Did everybody get that? So let's put this in form of a protocol. Okay? So Alice and Bob, this is even better. They can even ask Eve to supply their state, right? Because she can either be honest and just give them the state they want and then have no information about the state they have, or they can prepare the state with the third copy, so she has her copy of the state, but then Alice and Bob can detect it, right? And so you can even assume the bad person to run the protocol, if you like. So they ask Eve to distribute n of these copies in this. They want it in this singlet state, the 2-particle state, psi2, but they don't know if Eve complies to their wish or not. Okay, now they pick a subset of these n copies, say m, and you pick the subset randomly and do either and do z and x measurements on these, and they always do the same. Either they do both x and they both do z, and they announce the results publicly. And if Eve has really prepared several psi2 states, then the results will always agree. So they do this m times, and they announce the results, and they can check if they agree, no matter whether they measure x or z. If they all agree, they can be sure, or at least sure with a certain probability, that Eve has honestly prepared the state and not prepared something else. And then they announce the results publicly. If they agree, they know they really have psi2s and not the ones with the third copy. And then they can use the remaining qubits do the measurement both of x or both of that without announcing the result as their shared key and run their classical one-time pad crypto protocol on this. Okay, so that is important. So this protocol has 2 stages, and in the first stage, they can check whether their state is correlated with the state that Eve has or not, because the correlation with Eve's state in the quantum world leaves traces behind in the 2-particle state. You all look confused. Okay, but this was the main message, right? I have a protocol. Okay, so let me repeat it. I have a protocol, and the thing is, I can do a test. The quantum states, when Eve copies the information, she has to hurt the state, and this can be detected by Alice and Bob, and they can detect that there has been a copy. And then they know they cannot use this key for secret communication. Okay, this is complicated, but this is the essence of quantum cryptography. And you might have heard other explanation of this before, and if it didn't have this step, then it wasn't an explication of quantum cryptography, because then it was just an explication of the thing with the socks, the classical protocol. So the thing is really, the new thing is you can detect whether there had been a third copy. Okay, let's quickly go through this experiment that I did here. So I claimed there is no classical machine, and I want to argue that, but there is a quantum machine. So remember we had these 3 gentlemen here operating the apparatus, and I claim the following quantum state does what I want. The state that is either up, right, up, right, up, or right, up, up, minus right, right, right. And when they put the handle in the left position, they measure they measure Z, and in the right position they measure X. And if you go through this, if all three of them, remember the product of three A measurements was always -1. So if they measure Z, 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 they should always get -1. Should be Z, Z, Z eigenstate. So this one gets plus times -1. This time one gets plus times minus times plus. This one gets minus times plus times plus. So all of them have 2 pluses, 1 minus, product being minus, and here you have 3 minus 1s multiplied together give another -1. So indeed, if they all measure Z in this state, they all get -1. So, and the other thing was if two measured B, which now is X, two measure X and one measures Z, the product should always be +1. So what happens if I do X, X, Z? So X and X, so I get this one gets flipped down, this one gets flipped down, and this one gets a -1. So I have minus down, minus right, 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 and this is minus right, right, right. So this one gets flipped with this one, and you can also check that these two get flipped under this operation. So indeed, as you can see here, +1, -1, -1, and I have 1A and B. Indeed, the product is always +1. Okay, and so this quantum experiment realizes what I claimed before for my experiment, what the outcome was. And classically, I argued it's not possible, but here it's a local measurement. Each one just measures on their own qubit, and they get this result. 3 Z measurements always +1, one Z measurement, 2 X measurements always +1. Okay, so this experiment really shows that you can do things in a quantum world that are impossible in a classical world. And in particular, if you're philosophically minded, this proves that quantum mechanics is not secretly a classical theory. You could imagine that deep inside the microscopics are little wheels and things that turn and operate electrons and atoms and everything in a way that they look like they have this weird quantum randomness. But this shows whatever the gears inside are, you can never reproduce such an experiment. With the secret classical mechanics. Okay, I said I'm not going to talk about quantum computing. Let me just mention 3 things, entry points to Wikipedia, if you like. 3 famous algorithms. Grover's algorithm is a database search which gives a quadratic speedup compared to the best known classical algorithm. Shor's algorithm is about factorization. That's the one with 15 being 3 times 5. That gives an exponential speedup, and similarly Simon's algorithm. So I copied this from the web. So now we're talking complexity classes, right? BQP is bounded quantum polynomial. These are the things you can do with a quantum computer. And this set is bigger than the P problems, the one with polynomial runtime on a Turing machine. This contains some NP problems, even contains some problems that are just in P space, but not in NP, but it does not contain NP complete. So even with existing quantum computers, you're not going to solve, that's conjectured, right? Nobody knows whether these are really different. Okay, but current state of the art, current belief is that the quantum computer does not help you with solving NP complete problems. Okay, I said I'm not going to talk about this. Rather, for the last, hopefully a bit amusing 10 minutes, I want to discuss this question, is the human brain a quantum computer? Because I have been discussing this question with friends over at least the last 15 years, and maybe you've seen this book by Roger Penrose or one of the other popular books by Roger Penrose, where Roger Penrose is an important physicist in the theory of general relativity and quantum gravity, but he has written lots of popular books, really thick ones, And he advocates the idea that the human brain is such a great machine, it can solve so difficult problems like proof theorems and whatnot, that no way it can ever be a Turing machine. It has to use the quantumness because deep inside the brain, quantum processes, blah. Okay, so let's investigate this. So let's summarize this 600-page book. And the brain can do more complex things than it can do on any computer, right? So let's investigate this idea a bit. So is the human brain a quantum computer? Well, the answer is obviously not, right? This is a brain, this is a quantum computer. Okay, but maybe that wasn't the answer he was looking for. Maybe we should. The next obvious answer is obviously yes, right? It consists of atoms and molecules that are governed by the laws of quantum physics. Basically, that's the argument that Penrose advocates, right? But so does a silicon-based computer. I mean, this is a memory chip, and this is the band structure that you use for the semiconductor properties of the silicon or whatever technology you use semiconductors, and this thing is the band structure, and that's the result of a quantum physics calculation, right? So my MacBook that runs this presentation is a quantum computer because it uses quantum properties of silicon. Well, that's also not the answer. Then every computer is a quantum computer. Okay, so next answer is obviously not. So I mean, the lesson we learned from the previous slide was this question is not really about how the thing is made, right? The question is, what kind of problems can I solve with it? Are the problems that I can solve with a brain different from the problems that I can solve with a classical computer? And I mean, for a classical computer, I don't want to discuss MacBook Pro specs, right? I want to discuss whether I can solve the problem with the Turing machine. So the question is whether I can simulate one thing with the other, right? So the question is the human brain a quantum computer? Is really the question, can I simulate the human brain, in theory, right? On a classical computer, on a Turing machine, can I, or can I, and thereby solve all the problems that the human brain can solve, or can it do more, right? And then the answer to this question, if I interpret this question, is the human brain a quantum computer as, can I simulate human brain on a big enough Turing machine if I have enough time? Then the answer is again obviously yes, right? Because as I said, sorry, let me put it again. If this question really reads, if I can simulate it with a Turing machine, then it's not better than a classical computer, and then in the sense of this question, it's not a quantum computer, right? Then it's as good as a classical computer, or at most as good as a classical computer. I would have to show that I can emulate a Turing machine on my brain, right? To show the opposite direction, right? But the answer is obviously not. This is Schrödinger's equation. In short, this is the equation that governs the physics of my brain, right? This is how the quantum state psi evolves in time. This is now a bit more than a 2-qubit state that you have to simulate 10 to the 23 electrons in my brain, but I'm terribly convinced that, this is a partial differential equation. It's huge, right? But I can always numerically solve it to any accuracy that I like, given my computer is big enough and have enough time. So, whatever quantum processes happen inside the atoms of my brain, I can always simulate in principle, all the electrons in my brain, and that on a classical architecture. And therefore, I won't be able to do anything fancy, more fancy than I can do with the Turing machine. But again, then I could apply this to any quantum computer, right? I can also, I showed you the picture of this optical setup, which is supposed to be a quantum computer, and I could also simulate this on my classical computer. And okay, so the question is not really, the question is not really whether I can at all solve the problem or not. Like, even if I have a traveling salesman problem with 2 million cities, it has a solution and it takes a finite amount of time on a Turing machine. It's long, right? It's a huge, it takes very, very long, but specific problems always O1 in time, right? It's a certain time, it's bounded in time. So it's just when I vary the number of cities, the question is how it scales. So the question is, can I effectively simulate a brain on a classical computer or not? And there the typical question is whether it scales polynomial. And to that answer, I have no idea. But at least get the question right. I think the correct question, if you want to ask, is the human brain a quantum computer? The correct question you should think about is, can I simulate n brains effectively with the number of Turing machines that is polynomial in n, right? So I send n to infinity and study this problem. This is really the problem that you want to investigate if you want to decide if the brain's a quantum computer or not. All the other understandings of the question, as I tried to explain, are completely meaningless, and therefore I think also Penrose misses his point, because he's not investigating this question. Okay, that's all I had to say. Okay, thanks for not all falling asleep. Okay, I should say many thanks for Schneider from Munich CCC for setting up these red and green lamps yesterday at night at 2 o'clock in the morning. We can have probably 1 or 2 minutes of questions now, but if you have more urgent questions, send me an email, Twitter, DM me, or go to this is my blog that's terribly out of date, but I discuss all kinds of physics questions. You can find also the discussion of is the brain a quantum computer question in this blog. Okay, any urgent questions now? Urgent questions now. Okay.
Okay.
One person is not asleep enough to ask a question. Yeah. So you shout and I repeat your question. Okay, just shout. I repeat what you say. To exchange keys, you usually want to, you said.
Thanks. You usually want to exchange keys because the public communication channel is not reliable and you want no eavesdroppers. So is there a possibility to improve that key exchange theme to even on an unreliable public channel, where the man in the middle can also modify the bits you want to compare in order to check whether you received the same measurements?
Okay, did everybody get the question? What about when I cannot trust the public channel? So remember, I had to announce my results publicly, like I put them in the newspaper. Alice says, Berlin, CCC, Alice says, I measured X and all I got was -1, right? And I have to trust that this is really what Alice measures when Bob reads this. And the question is, can I do without this? And my answer is not that I know of, and I think you're completely screwed if you, that effectively means you cannot exchange any information, right? And then, even if you can't exchange the cryptotext, then, right, that's what you want, right? You have to exchange the cryptotext. If you can't do this, yeah, then I would say you're lost. You can always authenticate your public channel and stuff, but you can sign it, but if it's unreliable in the end.
Okay, thank you. Sorry, we don't have time for other questions.
Thanks.